So we've dealt with collisions in one dimension, but now we have to deal with collisions or conservation of momentum in two dimensions. Often 2D is going to involve an explosion, which is kind of fun because they're going to go off in any different direction. And the key is that we got to bring in our knowledge of vectors and pay attention to what the overall vector is for the momentum afterwards. So here's an example. A large snowball is traveling at 5 meters per second parallel to the x-axis, and it collides with an even larger snowball traveling at 4 meters per second parallel to the y-axis. If the two remain together after the collision, determine the magnitude and direction of their velocity. So we're going to do the same thing where we do the momentum before equals the momentum after. Momentum before the collision equals momentum after the collision. The only thing we're going to do is we're going to do that for both the horizontal direction and for the vertical direction. So let's separate this into components for a second. They're stuck together, so this is the momentum of them in the y direction, and this is the momentum of them in the x direction. So in the x direction overall, before the collision, we only had this one. So that momentum is 2.5 times 5, and that's the only momentum in the x direction before the collision. And then after the collision, the momentum in the x direction is just this component, which is the momentum of them stuck together in the x direction. So they're stuck together, and that means that they have the total mass would be 7 plus 2.5, which is 9.5. And then they have a velocity, some sort of velocity. Now that's the overall momentum, the mass times the velocity, but we're doing just the x, so that would be the cosine of the angle. That's in the x direction. Now in the y direction, very similar, now we only have this one involved. So we have 7 times 4 equals 9.5 v sine of the angle. Now we have two equations and two unknowns, so we can use our handy-dandy algebra skills to solve them. So solve for either the velocity or the angle, and then you're going to plug it into the other one. So we're just going to rearrange one equation. So let's do, doesn't really matter, we'll do the x one. I'm going to solve it for v, I think. Let's see how that goes. So 2.5 times 5 divided by 9.5. So we're trying to get v by itself. So we get v equals 1.3 divided by cosine of the angle. We're going to plug that in over here. So we get 7 times 4, so 28, equals 9.5 times v, so v is this guy, so 1.3 over cosine of theta times sine of theta. Now, your life will be much easier if you know that sine of theta divided by cosine of theta equals tangent of theta. So let's get tangent of theta by itself, and then we divide the other ones onto the other side. So we take 28 divided by 9.5 divided by 1.3. So we get tangent of theta equals 2.267. Take your inverse tangent on your graphing calculator, and you get 66.2 degrees. And then you're going to plug this back into either equation. I'll just plug it into this one since it's already arranged for v, to solve for what your velocity is. So we get v equals 1.3 over cosine of 66.2. So you get 3.25. So your answer is 3.25 meters per second at 66.2 degrees. Alright, let's look at another example. A 1,200 kilogram truck is moving at 9.6 meters per second towards 270 degrees, And it collides with a 850 kilogram car moving at 15 meters per second towards 180 degrees. So 270 degrees is just straight down. So the truck's going this way at 9.6. The car is moving towards 180, so that's this way. And it's moving with 15 meters per second. We want to know the direction and magnitude of their velocity after their collision. So let's just draw an arrow to show, it's going to go at some sort of angle because they're going to get knocked off course probably. So if we separate this final momentum into components, then we can see that we've got a horizontal direction before and after and a vertical direction before and after. So horizontally beforehand, you only had this momentum. So that one is 15 is the velocity and 850 is the mass. And then that's going to equal the momentum afterwards, which is just the x component of the final velocity. So they're going to stick together. It doesn't say that, but it means that. So we've got 1200 plus 850 times v cosine of the angle, because that would be this x component. And then in the vertical direction, that's only this guy. So you've got 9.6 for your velocity times 1200 equals 1200 plus 850 v sine of theta. So we've got two equations and two unknowns. So I'm going to erase this so I have some space to work. Just to remind myself the arrow that I marked and with this angle marked. Okay, so we have 12,750 equals 2,050 v cosine of theta. So we have v equals 6.2 divided by cosine of theta. And we're going to plug that in for v in the second equation, which we have 5.6 equals, that's what all of this is equal to. So I just moved everything to the left side, all the numbers. Now I'm going to plug in all of this for v. So I have 6.2 over cosine of theta times sine of theta. And by now we should all know this is what? It is tangent of theta. So we have 5.6 equals 6.2 tangent of theta. So you take 5.6 divided by 6.2, which is 0.9, and then you inverse tangent, and you get that the angle is 42 degrees. But we also want to know the velocity, so plug that back into the one where you already rearranged it for velocity. And you get v equals 6.2 divided by cosine of 42. So that's 6.2 divided by 0.74. And you get 8.38 meters per second. So your answer is 8.38 meters per second at 42 degrees. Alright, here we have an explosion problem as promised, and it's exploding into three pieces. So we're still going to do horizontal and vertical, but since this is an explosion, then the left side is 0 because it started as 0 for both of them, so that's easy. We need to break both of these up into components, and this last guy. The total is 100 grams, and the first piece is 35 grams, and the second piece is 45. So this third piece is 20 grams times some sort of velocity would be its momentum. So this component is 20v cosine of theta, and this is 20v sine of theta. It already solved the momentum for you. How nice of it is that? So this side is 2800 sine of 50 and 2800 cosine of 50. And this one is 3435.3 sine of 45, because that's my angle right there. And this side is 3435.3 cosine of 45. So, in the horizontal direction, we have 0 equals, and then we're going to add up any of the horizontal ones. So, we have cosine of 50 is 0.64 times 2500. So this component is 1607. So that one is going this way. This one's also going the same direction, so we're going to add that one. So it's cosine of 45 times 3435.3 gives you 2429 minus, because this component is going the other way, although that's only if you make sure you mark, okay, so we're marking this angle. The reason why I did the 45 over here is because then I could pay attention to the direction myself. If I did 315, it would take into account the direction for me, and I wanted to do it myself and just make sure I was doing it right for myself. And then, so we're going to minus 20v cosine of theta. So we have, that's only, so that's the two unknowns, so we need the other equation in the vertical direction, which is 0, so there's a different equation. I'm not just simplifying that first one. We've got 0 equals, this component is going up, so it's sine of 50 times 2800, which is 2144.9, minus this component, which is going down, which is sine of 45 times 3435.3, so 2429. And then this one's in the positive direction, so we'll do plus 20v sine of theta. Now we have our two equations and our two unknowns, so we get to solve for them. So take the first one, and I'm just going to simplify it some. 1607 plus 2429 divided by 20. So V equals 201.8 divided by cosine of theta, which we can plug in for V in the second equation. So we have 0 equals negative 284.1 plus 20 times 201.8 divided by cosine of theta times sine of theta. We have our lovely tangent of theta. If you ever end up with the cosine on the top, cosine over sine is secant, or just 1 over tangent works also. So then we have negative 28, not negative. I'm going to move that one to the other side. So we get 284.1 equals 20 times 201.8, so 4036 times tangent of theta. So take 284.1 divided by 4036, and then if we inverse tangent, we get that the angle is 4 degrees. Alright, so that gives you an introduction to momentum in 2 dimensions. It's not that difficult once you see it's just separating the horizontal and the vertical, and you're still just considering the momentum before equals the momentum after. And I'll see you later.